move on to the second half, okay, of the lecture. All right, not a lot left. Okay, I think it's pretty much we are trying to utilize what we already understand about the potential and potential energy, and then we'll just come back and then try to use it again and make sure that you understand the difference between the potential and potential energy. These two words are very bad because you have to focus on the word energy. Is there any the word energy in it or not? All right, so that's pretty much what distinguish the two. Okay, all right, but now everyone knows they are closely related. Potential is just the energy per unit charge, so they are pretty much the same thing. Okay, so let's come back here. So I'm going to try to talk about the potential energy from the perspective of knowing potential. All right, that will help. Okay, so what I'm trying to say is, if we starting from knowing the value of the potential, okay, and then you want to go back and calculate how much energy required to do something, you should be able to do it. So it's like what we are doing over here is just going backward. So the idea is you're starting from calculating the potential first by using that KQ over R. And then once you want to get to the potential, all you need to do is just multiply the charge that you want to go through that potential difference. You guys with me? Okay, start one more time. The potential, we know how to calculate. So if you want to compare between two positions, then you're going to lead to, that is going to lead you to potential difference. Okay, so this one is a potential difference. And once you know the potential difference between 2 points, this will lead you to knowing how to calculate the change in the potential energy. Required. Okay, sounds good. All right, so that's why we just say all you need to do is just take the charge and then multiply by that potential difference that you got before. So many arrows right here. Okay, all right, this is what it is. There you go. Okay, so we're just sort of going backward from knowing what are those potentials at different positions. And then we're just going to attack the problem about potential energy by simply multiply by the charge that gets moved between potential difference. All right, I think it's easiest to just take a look at the example and then it will be clear. Okay, so let's take a look at this one. Okay, so let's do well, I'm not sure we call it a simple one or not, but this is something that you can do right away. They say, if you have a system that looks like this on the left, okay, there are two charges right here, 5 microcoulomb and negative 2 microcoulomb. And they say, hey guys, can you find the work to bring 4 microcoulomb? So that's another charge, not on here, from so far away to this point P. How much work, how much energy you have to provide to this 4 microcoulomb charge for you to be able to take the charge from infinity and drag it and place it at point P. That's the whole question. Okay, so the answer is very simple. To get to the energy, first you calculate the potential first. And it's going to be potential, the difference between the starting point. This is your initial point. You want to starting from so far away, dragging from super far, and you're going to end up at point P. That's your final point. So what you wanted, you want to figure out the potential difference, right? The delta V. But we already emphasize on what does it mean by the difference. You take the final minus the initial all the time. Okay? And because it's going to be the potential at point P, that's your final position, subtract by the potential that you're starting from, which is so super far away. Okay? And the nice thing about this one is, this one go to 0. the V at infinity. That's what we agreed on. Okay, we agreed that when you are so far away from all of those charges, there's no effects from those, and we call potential zero. So the key conclusion is, you know that coming from, starting from infinity, you want to bring it to point P, potential difference is going to be V at P. And the V at P, now we know how to calculate it, is going to be K Q1, which is, you can call this number 1, and you call this number 2. So it's going to be K Q1 over R, and the first R is 4 meter. And then you add on top of that K Q2 over R2, its own R. Okay, I think I write this one very curvy, not nice. Okay, that's your, there you go. Here we go. Okay, you guys with me? Okay, so V at point P, okay, let me put an expression right here if you want. So it's just K Q1 over R1 plus K Q2 over R2. That's what it means. Just like what we did before. So all you need to calculate is just the potential at point P according to this. And this is, okay, this is a worked out number for you already. It's already right there. All right, now here comes the last step. How can you calculate the amount of energy or the amount of work that you need to do on the 4 microcoulomb charge? All you need to do is just take that 4 microcoulomb, yeah, multiply by the potential difference. So let me write it on the side right here. This is going to be Q times delta V. With me? It's going to be the charge multiplied by the potential that's changed from the initial point to the final point. But we already calculated that the change of the potential is just V at point P. And that's it. Final steps looks just like you take the charge, multiply by the potential at P. Whatever you get is in the unit of joule. Done. Woohoo! So I hope you understand what it means now by, you can now trace back to the amount of energy that required to move a charge from initial point to the final point. Okay, you first calculate the potential difference. Once you have that, take the charge that you want to move, multiply by that potential difference. You get back the energy required. And in this case, the work done is positive. What does it mean? It means you have to give something to the charge. So it means you have to drag it yourself. However, there might be some cases that the work done is negative. What does it mean? It means you don't have to drag it, you let it go. It will just move it by itself. Okay, something actually, the charge actually give away the energy. So the sign is important in this scalar business that we are doing. The potential can be positive or negative. The work done can be positive or negative. You have already seen this from thermodynamics. The work done can be both way. Yeah. All right, very good. All right, but I hope you see what's its relationship, yeah, between potential and potential energy. Okay, let's give it a shot. So if you can get to this one, I think this is another kind of questions that will show up in the exam, testing your understanding about the potential. And if this is good, then I think we can call it done. I think. All right, so it's gonna be quite short lecture today. I think this is very nice. Okay, in the rectangle of the figure, all right, so let's go through this one slowly because I want to make sure that you understand the whole process. All right, this one is a good exercise going from the fundamental of potential calculation down to the energy calculation. So the sides have length given 5 centimeter width, 15 centimeter length, 15 centimeter long. And the Q1 and Q2 are also given. Everything is good. V is 0 at infinity as usual. What is the electric potential at the corner A and B? That's your first question. Second question, how much work is required? Sorry. How much work is required to move a charge? The third one, which is not on here, Q3, which is 3 millicoulomb, 3 millicoulomb from B to A along a diagonal of the rectangle. B, drag it to A. That will be your third charge, Q3. But that can be done later. Okay, so there are pretty much 3 questions right here. First 2 questions is about calculations of the potential. And the third one is traced back to the amount of energy required. All right, you want to get ready? You want to go through this one together right now? All right, let's do an easy one first. Part A, what is the potential at point A, the corner A? Well, no big deal. You only have 2 charges that generating the potential right now is the Q1 and Q2. So I'm going to say K, Q1 over, okay, the distance from Q1 to point A is 15. So let me put in an SI system, 0.15 meter. I can just write the number right here just to make it clear. What is the length I'm talking about? So is it going to be K Q1 over 0.15 plus the influence from the Q2 charge is going to be K Q2 over, now the distance is going to be 0.05 meter here. It's going to be 0.05 meter. Okay, guys, cool. All right, so because we want to go through this one, so let's work out the number a little bit. So it's going to be quite nice to see the whole thing worked out. K is constant, 9 times 10 to the 9. Let me omit the unit so it won't get complicated here. All right, and I'm going to pull that K factor out to the front. So what's left to be added is going to be Q1, 5 milli is 10 to the negative 3 coulomb over 0.15 meter plus Q2 is, oh, I'm sorry, Q1 is negative. So don't forget to put the negative sign there too. So Q1 is a negative 5 millicoulomb. Q2 is positive 2 milli. So it's 10 to the negative 3 coulomb divided by 0.05 meter. Here we go. All right. So how good is this number here? Wow, is it nice? Not so nice? All right. Anyway, okay, let's go through this a bit. It's gonna be 6 minus 5. Oh, that's not too bad. Okay, so it's gonna be 9 times 10 to raise to 9 times, I think, okay, it's gonna be 10 to the negative 3 over 0.15. Okay, volt. Okay. All right. I think I get the numbers right. Okay, very good. All right, just leave it here. Not too bad. It's very close to the end result. You guys can, make it cleaner from here, but that's serve my purpose here. Okay, part B, it's pretty much the same thing, but now you want it to be calculated at the bottom left corner. Okay, so let's go through this. V at B is going to be, okay, start from the Q1, K, Q1. Now the distance is 5 centimeter. So it has to be this length that you used in the first term. Plus the influence from the Q2 to point B, which is now you need to use this length over here. So it's going to be 0.15 down here. Okay, so the numbers are different, of course, because it's possible you are at the different points. So potential in general should be different. Now you can work out the number once again. Okay, the number will look pretty close to what you had before, but you can just figure out again. Don't forget the sign. Q1 is negative 0.05 plus 2 times 10 to the negative 3, 0.15. There you go. All right. And at the end for point B, you getting, okay, let me work out the number a bit. So it's the negative 13 times 10 to the negative 3 over 0.15, something like this. All right. Okay. And it's negative, which is fine. So it's just saying that the potential at point B is still below 0. Okay, don't worry about the numbers at the end. You can actually punch the calculator if you want. You get the final numbers out for V sub A and V sub B. Okay. All right, here comes the final questions. How can you calculate the work that is required to move a charge, the third one, from point B, they say from point B to point A. All right, this is the last portion here. So part C, which is not too bad now, if you understand everything, that what they need is the amount of energy, right? The work done. Yeah, the amount of energy is the work done that you have to put to them. So it's going to be the charge that you want to drag, you want to move, which is Q3. And all you need to do is just multiply by the potential difference. That's it, done. So that means it's going to be Q3. The difference is always final minus initial. That's all the time. Okay. And because you start everything from point B, you end everything at point A in the travel at point A. So it's going to be VA minus V sub B. And that's it. You already know what the V sub A is. You already know what the V sub B is. All you need to do is just plug in the number and you're done. Is it? This is how simple it is. Once you already know how to calculate the potential and potential difference, going back to energy calculation is straightforward. Okay, one thing that you notice is eventually you get positive number. You see that? Going from B back to A, you get a positive work done. So it means there must be some work need to be done bringing the charge from point B to point A. Why is that? Because here, point B is lower potential. This is higher potential. With me, guys? So it's the same idea. If you want to bring an object from a lower potential to a higher, you have to bring it up. You have to work on it. So that's why the W that you get from part C is going to be positive. If part C flip the questions like, hey, what is the work done going from A back to B? You're going to get a negative number. Why? Because it's like you're rolling things downhill, right? You want to go from higher to lower. All you need to do is just let it go. But I mean, of course, you don't want to let it go freely. You just have to pull it, just like something is rolling downhill. You don't want to have it run out. So you just have to hey, hang on to it. So you apply the force opposite to the direction of the something that's dragging it down. So that's what it means. But at least you understand what it means by potential difference. When you want to go from low to high, you have to provide some energy to it or doing some work. You go from high to low, actually the system itself, I mean, the electric field can actually perform the work itself. So what you do, actually, you have to sort of hang on to it. So you do things in a negative direction. All right. Sounds like a understandable concept. All right, but that's what it means by, that's what it is that I'm trying to show you, the relationship between the potential and potential energy. These are the two words that I think it annoys many people. It would be nice if we define potential to be some other term so we don't get confused about potential energy and something. All right, but this is good. Okay, so if you guys okay with this, I am going to finalize today's lecture with this. All right, and once again, okay, from what you have done so far, you start to see why I said, even though you don't really get the whole sort of like derivation or verification of the formula, you still be able to do the problems of the potential and potential energy very easily, because either the formula or either the way of calculation is straightforward enough, You don't have to worry about vector. All you need to do is just apply the KQ over R and do the summation. But the last stop is this. All right. I don't think this will be in the exam. Oh, well, I wouldn't say that. Well, the understanding of this one is not in the exam, but the way of doing this is simple enough that if it shows up in the exam, once again, you see that Ajahn is like a single formula again. And when you look at this box right here, can you see that? This relate the electric field and the potential. Electric field, potential. Electric field, oh, this is supposed to be Z, potential. So this expression gives you back the electric field once you know what the V is. Isn't that cool? When I say isn't that cool, this is what it is. And I want to say that the reason that this is so easily calculated is because of this. All right, think of it this way. All right, I think I have an easy way to introduce to you this. Okay, all right, that's the, let me show you this. I think I need some space here. All right, so think of it this way. In the gravity, okay, that is your G, right? Okay, that is your gravity. Okay, but then you just said, Ajahn, if I am at some height, you can call this zero height. Okay, and sometimes you can go up, you can call this like maybe 1 meter if you want. Okay, wait for the screen a little bit. Okay, that's zero height. And then you can draw another line, yeah, horizontally. You get that's 1 meter. You can go one step further, that is 2 meter, right? All right. And then you say, Ajahn, the potential energy is mgh. All right, I've been repeatedly talking about this one. Then I can do the same thing with, oops, sorry, same color. Electric field. That's what you agree, that I can do that. Okay. And what I have over here is, if I extend that layer of height to the electric field, the scenario will look exactly the same, because you already saw that the formula for the potential energy is the same, but changing mass to charge, changing field from G to E, and it is going to be this kind of form of the expression. Okay, all right. Now, I want to make things a little bit more mathematics, because everything in the vertical direction, you can say that is your Y direction. So actually what I'm going to turn is, I'm going to, hey, instead of calling this height, I'm just going to sort of like generalize this one a bit. I'm going to call this the Y direction, because that means you can adjust your height, your elevation to any height that you want. So you have a variable Y to adjust your height. Okay. Now here comes the trick shot that I'm going to show you. Starting from the potential energy, let's follow me a bit. If I differentiate, whoa, with respect to the coordinates that in there, I get mg. It's no big deal, John. Just derivative of y with respect, derivative of u with respect to y, dy by dy is 1, so y just disappear. I can do the same thing with the electric field. All right. But when you look at the formula in the red ink, do you feel anything? บอกให้อาจารย์ mg, that's kind of the weight, and the qe was just the electric force, and actually it's pointing down, both of them. So if we already said that, we say that the y is up, that's your positive y. Actually, it would be nice if I turn the negative here, and introduce this to be the vector that's going to be pointing down. You guys with me? So that's kind of nice in the sense that,อาจารย์, if I do the derivative of the potential energy with respect to the coordinates, and then I put the negative sign to it, then I can get back to the force that is behind all those potentials. However, because we already introduced the concept of potential, not energy, just pure potential, for the electric, I can do everything per unit charge. Okay, now you have to look on the right because I want to bring you one more step here. On the right, I can do one more step. If I divide through by Q, or simply say I turn Q into 1 coulomb, I get this. Oops, sorry. Isn't that nice? By setting the Q to be 1, I can turn the U into the V, and the Q on the right just disappear. And all I need to do is just take the negative sign in the front. That will give me back the electric field. Okay, I don't know you guys sort of like get my logic or not, but the reason I just want to show you by comparison instead of going through some, this is actually, it's calculus based problems. It's sort of like they call it the vector calculus, but because I don't want you to sort of get confused too much, but the key concept is this. Now once you get the V, you take the derivative of V with respect to the coordinates and you add a negative sign to it. That will eventually lead you back to the electric field. Seriously, that's nice. Okay, however, in reality, because we already said the electric field can point in any direction, it doesn't have to going downward all the time. It can point up, point down, point in the radial direction. So that's why you have to take care of three-dimensional possibility of the electric field. And here comes this formula right here. With me, guys? Yeah, look at this. Let me go through this one more time. See, if you want to get the electric field in the x direction, all you need to do is take the V and do the derivative just like what you did. But you pick to do the derivative with respect to x alone. That's why this is a partial derivative. For those of you that haven't done the partial derivative, don't worry. It's just the derivative that you take the derivative with respect to x, and y and z treat to be constant. So you don't care. You see like, hey, y and z is just numbers. I don't want to deal with it. Okay, and then once you're done with that, add the negative side to it. That will give you the electric field in the x direction. And then you say, if you want, hey, what is the electric field in the y direction? You take the V, take the derivative with respect to y alone. So that means you're going to treat x and z to be just numbers. Okay? And whenever you're done, put the negative sign in the front. That will give you the electric field in the y direction. And now you can guess what should happen to the z. You take the V, take derivative with respect to z. You treat x and y to be just numbers. Very good. Once you have that, take the negative sign in the front. That will give you the z components of it. Now, from this expression, can you see that now you have all three components of the electric field? And then you can say, hey, Ajahn, I can take those and combine it into a vector form of the electric field. So that means I can get back to the electric field from knowing the potential. And that completes the whole loop. We're starting from the electric field, get down to the potential, the field, get down to the energy. Energy, we introduced the potential. Now we go back from the potential, allow you to calculate the energy required to move the charge, and then eventually lead you back to the electric field. Okay, they are all related. It depends on which angle you want to talk about. Okay, sounds cool, guys. Isn't that nice? All right. So for those of you that might have done some calculus related to this, this is called the gradient of a vector. I mean the gradient of a function. When you do the derivative, partial derivative for each coordinate, that's doing the gradient of the function. And then what you have is it's the negative of the gradient. Okay, but anyway, the partial derivative with respect to each individual coordinate is the same thing as the gradient of that function in vector calculus. All right, and I will show you how easy it is to execute this. Believe it or not. Okay, let's give it a shot. Okay, you guys still, when you guys at home sort of follows the logic here. Okay, and this will confirm that even though you don't know about the vector calculus, you will be able to answer this problem. Here, they say, calculate the electric field from the electric potential that can be described by the function. There you go. So you are given the V. They say calculate the electric field, which is vector. So of course, the electric field vector is going to be E sub xi, E sub yj, plus E sub zk, right? Or if you want a bracket notation that you saw in the previous slide, same thing. It's just whatever you prefer to represent a vector. Okay. The screen is kind of coming up. Okay. All right. So that's what it means by you have to calculate the electric field, so vector. So we're going to attack each component at a time. So let's start from E sub x. Okay, the x components can be found from negative of the potential change with respect to x coordinates. So it's a dv by dx is a partial derivative of v with respect to x. And now I'm going to show you how it's done. Just keep the negative sign in the front, so make sure that we don't forget that. Now I'm going to take derivative of the v, but do it with respect to x. I'm going to treat y and z to be just a number. It's like it's not a variable anymore. So the first term, all I need to differentiate is just x. So I'm going to get 2x, and y is just a number, just there, no change. With me, guys? The second term, because you only have purely y cubed, but y is being treated as a number, 0. Gone. And the third one, you want to differentiate this. Z is just a number, so derivative of x is 1, so you are left with just z in the back. And that is done for the x components of the electric field. Oh, I think I know why the communication is bad. This room doesn't have a lot of signal. So that's why it's like why the screen is like refreshed so slowly. I can see now I have only 2 bars here. Oh, this is bad place. We should do the other side of the building, I guess. Okay, next time. All right. But you guys at home still all right? Not too bad for the screen updating, a little bit lacking, not too bad, yeah? Okay, all right, continue. I can do this for the y component. So it's going to be negative dv by dy. Yeah, oh, okay, yes. I have only 12%. All right, this is the last example, so I think I'm good. All right, negative sign is there. Okay, let's attack the first term. I have to take derivative with respect to y. X is just number, so it's there, x squared, no change. Derivative of y with respect to y is 1. So that's it, that's my first term. All right, second term is y cubed, which is After derivative, it's going to be 3y squared. Yeah, and the last term has no y in it. So x and z are treated as just a number. So it's 0 on the third term. Alrighty, last one, guys. E sub z. I'm just do negative dv by dz. Oh, not too bad. Negative sign is there. Take the derivative with respect to z. X and y are constants. So the first term gone. There's no z in it. Second term gone. No z in it. The last term x. Boop, boop. There you go. So you can do it sort of like make it a little nicer by just sort of, okay, get rid of all those zero, make it a little bit cleaner, but that's not much more. It's a bit cleaner. There you go. All right, and what else that we can do? I mean, or can be asked. Actually, this is done. You get all three components of the electric fields. That's complete. But maybe if I want, well, hey guys, what is the electric field at 111, for example? Okay, so I mean, I can pick a point now. But hey, Ajahn, I want to know at x, y, z equal to 111. What is the electric field? That's cool because you know everything now. All you need to do is just take the x, y, z value, plug into your electric field components. So the first component, you're gonna get 1, 1. So you get negative what? 3. Is that right? Yes. Okay, negative 3. Or in x, you plug in the 1 and 1, you get negative 4. Plug in the 1, you get negative 1. That's it. So you know exactly which direction of the electric field should point to at the position of 111. Okay? And also, I can actually ask, well, hey, Ajahn, what is, oh man, I'm not asking myself, I mean, I'm asking you guys, what is the electric field magnitude at 111? Well, oh, Ajahn, because we already know the vector of the electric field at that 111 point. So it's going to be just a Pythagorean theorem, negative 3 square, negative 4 square, and negative 1 square. So you know the strength or the magnitude, yeah, how strong of the electric field at that point. So by knowing this, you can start from potential function, drag it back to electric field vector. From that vector, you know everything of the electric field. And that's complete the whole thing. Yeah, all right, cool. All right, so as I said, I hope you feel a little bit sort of like, I don't know, relief that even though you don't understand deeply at this point, okay, by practicing a little bit more, that will give you more understanding in terms of the material of these topics here. However, in terms of executing or solving the problems, it's not too bad. Yeah, you can know, you can calculate the potential very easily. You can, from that potential, allow you to calculate energy quite straightforwardly, and it even allow you to get back to the electric field through this simple negative gradients of the potential. Okay, sounds good. All right, so guys, that's good. This one, I mean, for those of you that don't like this one much, that's okay. All right, but if you want to try, I think that is kind of like you can try this one, but it's going to be the same as the previous one, but it's just simpler because this one doesn't have any z component to it. So I think this is a good try, I mean, good exercise to try yourself, and then we can sort of go through this one once again, like before the final, to practice. All right, but other than that, I think, oh, we accomplished everything today very nicely.